Okay, let's do a two-dimensional motion example. That's not projectile motion, right? Two-dimensional motion, three-dimensional motion exists a lot of times. That's not just motion undergoing the acceleration of gravity. So let's just take an ant, which I've drawn here, on a very strange trip. And let's just say its acceleration is 7 centimeters per second squared, 60 degrees south of east, and its initial velocity is 4 centimeters per second, 75 degrees north of east. And let's ask the question, after, and this is really unrealistic, but after 10 seconds, what is the ant's displacement? And let's ask what its final velocity is. Displacement, let's call that A, and final velocity. Okay, so this is my ant. I have many ants, but let's just say that's one of them. Okay, so how are we going to solve this problem? Okay, so, well, think about it, right? We draw a picture. Well, we've already sorted, well, we haven't really drawn a picture. I'm going to go ahead and put the ant on a coordinate axis. Let's just put the ant to the origin. Doesn't matter where we put it. And the acceleration is, I'm going to draw the acceleration in this picture. The acceleration is 60 degrees south of east, and that's the acceleration vector. Its length is 7 centimeters per second, and its velocity, initial velocity, is 75 degrees north of east. Didn't draw this to scale, but that's okay. So this is the initial velocity, which has a length of 4 centimeters per second. The coordinate axis here is just for directions, right? North, south, east. Whoops, that's not north. Sorry, east, north, etc. Okay, so that's the ants. There's some indications about the things about the ant. Now, exactly where the ant is going, I'm not sure, because think about what's going on here. Right, the ant is starting off in this direction. I'm making it red, right? Starting off in that direction, but the acceleration is in that is down and to the right, right? So the ant must be sort of, I guess, going sort of in that direction eventually, something like that. So I don't actually have a good sense of where the ant will show up, but I think we can say for sure it's not going to be in any of the west quadrants. Okay, so let's go ahead and say, all right, that's the best we can do for a picture. Yeah, that's reasonable now that you think about it. Just imagine that the acceleration was the acceleration due to gravity, and you're throwing something. So just rotate the page, right? So the acceleration due to gravity is heading straight down, and you're throwing something at an angle up. Duh. So it's going to go like that. So that's got to be the aim. So that's just like projectile. I mean, it's like projectile motion, but it's in the plane of the page, right? It's in the plane of the Earth, the ant walking. But you can imagine if that was projectile motion, and again, the acceleration vector is gravity, so that points down. The initial velocity is up, and so the object's going to go up and come on back down, starting to go, eventually going close to the direction of the acceleration. Okay. So let's see. The first thing we do is draw a picture. Second thing is choose our directions, which we did. And we can certainly call east X if you want, and north Y if you want. But we could just stick with the north and the east directions. And then the next thing is to write down our equations and then identify what we know and what we don't know. So our equations, right, in the X direction, we've got delta X equals, what do we have in the X direction? Aha, right? But there is now acceleration in the X direction. So we have delta X equals 1/2 A sub X t squared plus V0 xt, right? We got to go back to the original equations for constant acceleration. V sub X equals V0x plus A sub xt. Vx squared equals V0x squared plus 2A sub x delta x. So that's for the x direction. And then for the y direction, we've got delta y equals 1/2 a sub y t squared plus v0y t vy equals v0y plus a sub y t, and vy squared equals v0y squared plus 2a sub y delta y. Notice that this is still a constant acceleration problem. So we can use the constant acceleration equations. If a, the acceleration, was not constant, right? I said it's, I didn't say the words, but a is a constant 7 centimeters per second squared in that direction, then we couldn't use the constant acceleration formulas in order to, and then this problem would be hard or impossible given what we know. But it is constant acceleration. So for those of you who are really astute, you might recognize that perhaps we've made our lives difficult, or perhaps we haven't. I'm not sure. But if I took the, hold on a second. Actually, I had to think about that for a second. If I took the direction of the acceleration as one of my axes, now that wouldn't be the north or the east axis, but if I did that, then I could just this would simplify to 4 equations, right? If I had imposed an axis on this, right, we have the northeast directions, but if I impose an xy axis on this and call this x and this y, then the acceleration is in the y direction and there would be no acceleration in the x direction. And we're back to the identical thing as projectile motion, where the acceleration is 7 centimeters per second instead of 9.8 meters per second squared. Per second squared, sorry. Hopefully you caught that. Instead of 9.8 meters per second squared, but everything else is the same, and you could deal with this just like a regular projectile motion problem. Then in the end, whatever answer we got, we would then have to figure out how it fits on the northeast axis relative to the xy axis, right? The xy axis is rotated from the northeast axis by 30 degrees counterclockwise. So then we'd have to, once we found the answer on the xy axis, we'd have to rotate that answer, put it on the northeast axis, rotate it 30 degrees. That may or may not be difficult. Instead, we'll stick with what we got. It probably is in the end not so much harder or even just as easy to simply use the axes and the 6 equations here that we've got. Hopefully that made a little bit of sense, that you could make this just into a projectile motion problem with a different acceleration. Okay, so let's go ahead and identify what we know and what we don't know. I'm going to write that in purple. So just looking at I'm just going to start with the first equation and look at each variable and go through all the equations and look at all the variables, right? Okay, so that's what we always do. So I'm just going to start reading them off, right? Delta x is an unknown. Delta x we don't know. That is actually one of the things we want to know because we want to know the final displacement. Delta x is unknown. A sub x, well, we know a sub x because it's the x component of a. We just haven't found it yet, but that is known. Let's actually go ahead and stop and pause and take the components, because remember, that's always a step that you have to do at some point, and it's probably easier done earlier rather than later. You always have to take the components of your vector quantities in order to do these problems. So as an aside, we'll take the x component and the y component of acceleration, the x and y component of acceleration, and you would find that a sub x is equal to a times the sine of 30 degrees. Go ahead and look at that triangle, figure out why that is the case. A sub y is equal to, and it's in the minus y direction, but the magnitude of a sub y is a times the cosine of 30 degrees. You can figure out why that is true. And a sub y points in the negative y direction. We have to use that later. Same thing with v0. v0 has a y component and an x component, and v0x, go ahead and do the geometry of the right triangle. v0x is equal to, the x component is v0 times the sine of 15 degrees. Sine of 15 degrees, and v0y equals v0 times the cosine of 15 degrees. And both of those are going to end up being positive. Okay, so this is just the geometry of the right triangle. I'm not going to do it out for you any more than that. You can figure out the x and the y components, the right triangles here, right, of the two right triangles that we drew on the graph. Okay, I've gone ahead and written out the components, giving you the numbers for the components, and we just got to pay attention to the directions when we write down their values for the equations. Okay, so a sub x is equal to plus 3.5 meters per second squared. T is equal to 10 seconds. We're asking what happens after 10 seconds. V0x is equal to 1 meter per second. Vx final, that's one of the things we're looking for, the final velocity. And those are all the x variables. The y variables, delta y, we're looking for that. Whoops, not 0. Looking for delta y. A sub y. Now this is where, if I had done this carefully, right, 6.1 meters per second, but it's in the minus y direction. So it's minus 6.1 meters per second squared. What else is left? V0y. V0y is equal to 3.9 meters per second, positive, making sure that we're thinking about I got to put in the plus or the minus explicitly to show that we thought about the direction. V0y and Vy. Vy is an unknown. So there should be 4 variables for each plus time, right? So 1, 2, 3, 4. 1, 2, 3, 4. Yeah, 4 variables for each set of equations plus time. And that's the 5th. So that's the 9th variable. So there are 9 things that we either know or need to find out. And you can even count the unknowns, right? There's 1, 2, 3, 4 unknowns. And that's with these 6 equations, that's the most unknowns we can have, 4 unknowns. Because this is only 4 unique equations when we are dealing with kinematic. The 3 kinematic equations, only 2 are unique out of each set of 3. Okay, so that being said, it is now a strict plug-in. So we're just going to plug in and find that. I'm going to start plugging in on this page, even though it's a little messy. You should not squish it up as much as this. You should give yourself plenty of space and be very clear. But I need to, just so you can see where I'm coming from, I'm going to start with this equation and start plugging in. Delta x is equal to 1/2 a sub x. I'm going to leave off units just for speed, but you should not make a habit of leaving off units. Plus 3.5 t squared, 10 squared, plus v0x, which is, looking for v0x. V0x is 1 plus 1 meter per second times 10 seconds. I just left off the units in order to be expeditious here. Let's just be careful. For what are we looking for? We're looking for displacement. Displacement is delta x and delta y, right? That's going to be the net displacement. It's going to have an x component and a y component. So I'm just going to go ahead and write the y equation. That's this one. Delta y equals 1/2. A sub y is minus 6.1 meters per second squared times 10 seconds squared plus v0y 3.9 times 10 seconds v0t. And that's going to be part A. We get evaluate that for part A. And then part B, again, it's a strict plug-in, really. Part B is just going to be taking v sub x, plugging in for that, v sub y, plugging in for that, and then that's going to give us the 2 components of the final velocity. So just plugging in the numbers, we get delta x is positive 185 centimeters, delta y is minus 266 centimeters. Be careful of your units, right? These are all centimeters. Vx is positive 36 centimeters per second, and Vy is minus 57.1 centimeters per second. Not quite finished. So just writing those two vectors in component form, the net displacement is 185 centimeters east minus 266 centimeters north. Be careful, right? It's not minus 266 south. It's the y-axis is north. I mean, if this, we could just write this as I hat and j hat. And so the minus just tells you that it's in the minus y direction. And the final velocity is 36 centimeters per second east, minus 57.1 centimeters per second north. So this gives you it in component form. I didn't ask for it in magnitude direction form. You know that you can take this vector, 185 centimeters, and minus 266 centimeters, and you can turn that into a displacement vector, d, and you can figure out, I'll leave that up to you to figure out. Same thing with the velocity. So again, just be careful. This is one of those examples I stressed in another class where you say, oh, it's minus 266 centimeters, so that's in the south direction. You are right, that's in the south direction, but it's still minus 266 centimeters north, which is south. So you could also, it is true that you could recognize that it's the south direction, so you could write net displacement is 185 centimeters east plus 266 centimeters south, right? That would be correct as well. And you can do the same with the final velocity. Okay, done with that example.